All right, welcome. I am back with the biochemistry lecture or lecture series. Although, as I mentioned in the Discord, uh, basically I'll be doing them solo from now on, not with basically teaching someone on stream, which is totally fine. Unfortunately, they couldn't make the commitment, which is fine. These things happen. But then now I'm going to try and do it basically on my own, essentially still ultimately the same format overall, but just, whoever wants to tune in as my students or whatnot. And while I'm always trying to constantly sort of tweak and see how I can make it better or improve it. Or again, if it's just totally worthless, then maybe eventually I'll stop doing it. But I don't plan to, at least not for the foreseeable future, since actually I quite enjoy making the presentation and fleshing out, how I'm going to try to get this concept across to hopefully a broad audience, or for anyone that doesn't have, let's say, a science or biochemistry background. But yeah, that's the plan now for, let's say, the weekly lecture series. So, we're on lecture number 6. We're on chapter 2 now of the textbook. So let's see if I can set this up. I'm sort of revamping my setup. One moment. Okay. Let's see. And yeah, well, so unfortunately, since there's the drawback of like I'm not interacting with someone in real time, like as my whatever student, quote unquote. But as I mentioned in the Discord, on the plus side, I can pay more attention to chat, and if there are questions in chat, I can hopefully try to answer them as best I can. And so yeah, it's been a little bit of a delay. I think the last time I did one of these lectures was about at least two, if not 3 weeks ago. But yeah, now hope to be back now for the weekly moving forward. At least for like the next little while. I'm sure there's going to be something that comes up that forces me to postpone. But yeah, I'm trying to stick to weekly. So picking up where we left off last time, I'm gonna lower my music a little bit if I can. I think that's a little bit better. Okay, yeah. So picking up where we left last time, and yeah, so I only plan to, whatever, lecture for an hour, since, I have to sort of conserve slides. 1 second. Yeah. I cannot necessarily, like, go through every single slide that I've prepared, because it actually takes quite a bit of time to prepare the slides. And so I want to make sure that, I leave myself enough time to, like, make new slides as we go. So I try to limit it to, like, an hour, so that, week to week, preparing an hour's worth of slides is not a huge amount of work. Since, I'm technically doing this essentially, unpaid. So, picking up where we left off last time, okay, we were talking about polarity, and we covered polarity quite a bit. And so I've went through this slide before, okay? But polarity is important to understand, the chemical properties of the amino acids, but also how they behave and dissolve in water. So right now we're covering the amino acids, and we've gone through all 20 of them, but we'll be seeing them over and over again. And it's important to at least, to fully understand and appreciate how the amino acids, behave and, interact with, let's say their environment or other amino acids. This concept of polarity is pretty important, but this is something that we'll be revisiting over and over, and I'll be reminding over and over. But there is this principle in chemistry that we say, like dissolves like. As in, if you're a polar molecule, okay, you will dissolve in other polar molecules. The example that I gave last time, on stream, was like when you dissolve salt, when you dissolve sugar in your tea or coffee, or even just in water, Okay, the salt dissolves, the sugar dissolves, uh, and that's because salt and sugar, those are well, salt technically is like a super polar molecule. Okay, it's, let's say, extreme polarity, but sugar, for sure, table sugar, that is a polar molecule. And since water, as I've shown here, that is a polar molecule, then sugar dissolves in water. And so, as written out here, polar molecules dissolve in other polar molecules, and non-polar molecules dissolve in other non-polar molecules. And this is why we say the non-polar amino acids are hydrophobic, as in, since they won't dissolve, okay, they won't dissolve in water, they are essentially, afraid of water, so to speak. And this is an important principle that we will see over and over, throughout biochemistry or biology. There is a specific phenomenon called the hydrophobic effect that is super important. But yeah, just introducing these concepts and trying to reinforce them as we go. And so yeah, water is a polar molecule. Okay, it's a very important polar molecule. I think virtually everyone now knows that water is critical for life. And there are many reasons for that we will get into. But yes, there's this aspect of polarity about water that is important. So we went through this last time and just reviewing a little bit. Okay, so we have been covering the amino acids, and we're going to start, assembling the amino acids together. Okay, connecting them together to make a large protein. So, and as I guess I covered 2 or 3 weeks ago, there's ways of classifying the amino acids based off of their chemical properties. Okay, and so this is one way to classify this set here. Okay, asparagine, glutamine, serine, threonine, tyrosine. Okay, they fall under the category of uncharged polar. Okay, as in they do not have full charges in their side chains. Okay, but they have partial charges on their side chains. Okay, and the example that I pull out here is the amino acid serine. Okay, that is an uncharged polar amino acid. And why is it uncharged polar? It is uncharged polar because of the oxygen in serine's side chain. And since the oxygen here, okay, it's surrounded by carbon and hydrogen. Therefore, okay, since the oxygen is way more electronegative than the surrounding carbon and hydrogen, it is able to, draw electrons towards it. Because, as we've covered previously, oxygen is a very electronegative that I'm going to also be covering a little bit more, should be today or in the next few slides. We're not going to do a deep dive on electronegativity just because it's not super critical to understand all the details, other than, electronegativity is a measure of, how much an atom can pull electrons towards it. But yes, this aspect, or this is a similar theme for the other amino acids in the table. They will have some sort of, electronegative atoms in their side chains that makes them polar. Okay, so they don't have full charges, they just have partial charges, and so they are polar molecules. And then there's this other way of grouping them. Okay, this is another aspect, or another way to categorize the amino acids, which is by non-polar. Okay, so in contrast to what we've seen previously, just in the last slide, okay, those are uncharged polar amino acids. Okay, and so they have partial charges in their side chains, and we've seen the other amino acids. Okay, where they have full charges in their side chains. Okay, what we call the charged polar. Okay, so pretty much the overall broad categories of the amino acids is charged polar, what we just saw in the last slide, uncharged polar, and then these ones here, which represent about half of them, or I think 9. 1, 2, 3, 4, 5, yeah, 10. These are the non-polar ones. Okay, so these amino acids have no charge at all in their side chains. And since they are non-polar, they are hydrophobic. Let me just go back to the last slide. Did I make a mistake? Not this one. Oh, okay. Yes. No, I didn't make a mistake. Double checking. I can make mistakes. But yes, these amino acids, okay, they are hydrophobic. These do not like to be in water. And they like to, as I just covered in a few slides ago, okay, like dissolves like. So the nonpolar like to stick with the nonpolar. It's kind of also the same principle of like, birds of a feather flock together. Okay, and so why? Why are these non-polar? Okay, well, the example that I put here is the amino acid alanine. Okay, so because the side chain of alanine is just carbon and hydrogen, which are basically not electronegative, then alanine is non-polar. There are basically no electronegative atoms in the side chain of alanine, which is, I've just circled there in purple, which is just carbon and hydrogen, which are effectively not electronegative. So there's no ability to pull electrons towards it, and therefore it's classified as non-polar. And so yeah, these non-polar amino acids will tend to stick together, and they will tend to want to be away from water because they are hydrophobic, which essentially translates to, afraid of water. And so why do we call them amino acids? I believe, I covered this 2 weeks ago, but just to reiterate the point again, we call them amino acids pretty much as a result of organic chemistry, where organic chemistry is, a discipline or a field in and of itself. It heavily, or there's quite a bit of overlap with organic chemistry and biochemistry, and well, pretty much all the branches of chemistry. There's some degree of overlap, but it is just pretty much a naming convention, okay? Where any molecule that has this arrangement of atoms, okay, that I've circled here, with you have an oxygen double bonded to a carbon, and then you have another oxygen and a hydrogen. So pretty much what's shown in red there, okay? When you have that arrangement of atoms in a molecule, okay, we call it a carboxylic acid or a carboxylic acid group, okay? And in a chemical formula, it's pretty much very often appears as COOH, as in carbon, double bonded to an oxygen, and then you have that OH group there, another oxygen and a hydrogen. And that's why this, they give the example here of pentanoic acid. Okay, we call it pentanoic because there's 1, 2, 3, 4, 5 carbons in it. And then since it has, okay, this carboxylic acid group, okay, we call it, or organic chemists call it pentanoic acid. And then there's this other, arrangement of atoms, okay, called an amine group, where pretty much if you have a nitrogen surrounded by, this R stands for pretty much, anything, or typically a carbon atom, just replace R with carbon. And then we call that an amine, or an amine group, okay? And so this molecule here, we call it diethylamine, where if you have this amine group here, somewhere in the naming of the molecule, you'll have that amine or amino or something to that effect in the name of the molecule. But all that to say, the main point is, it's pretty much, when you have this arrangement of atoms in a molecule, okay, we give it a name. And for this arrangement, we call it a carboxylic acid. And then for this arrangement, we call it an amine. And so this is why we call them amino acids, because you have an amino group, okay, the NH3+. Okay, so here the nitrogen is surrounded by 3 hydrogens. So just replace the R here on the left with hydrogens, and so we call it an amino group. And then here you have a carboxyl group. So here it's shown as COO-. So it is technically, or not technically, but it is essentially this arrangement of atoms, okay, but it's missing the hydrogen. It has lost a hydrogen. and so that's why we call it a carboxyl group. And so we call them amino acids because they have the amino group or an amine group, and they have a carboxylic acid group or a carboxyl group. And so amino acids is the name that we give them. Pretty much when you have this arrangement of atoms, okay, it's effectively an amino acid. So moving on, this concept of like dissolves like, okay, it's pretty important in not just chemistry, but biochemistry and biology. And so, we were talking about last time, on stream, like, okay, permanent marker, like Sharpies, okay? Well, if you've ever written with a Sharpie, okay, written on, let's say, some glass or plastic with a Sharpie, and then you try to get rid of it with water, and, actually, Tyler tried to do this on stream, of, like, wipe it away with water, and then wipe it away with isopropyl alcohol, okay? And no surprise, okay, when you try to remove, your standard Sharpie from glass or plastic using water, you're not able to get rid of it. But if you switch to isopropyl alcohol, then the Sharpie ink, wipes away really easy. Pretty much like dissolves right before your eyes. And so why is that? Well, it goes back to this concept of like dissolves like, where, so I actually went to the Sharpie website, okay, and they have this FAQ, frequently asked questions section. And so there's this question about, what is basically the type of ink in the different styles of Sharpies that they have. And yeah, no surprise, pretty much the primary ingredient in the ink is alcohol, okay? Whereas they say the principal solvents are alcohols, but they also contain ethylene glycol, monobutyl ether. All other Sharpie ink colors are perm chrome ink, which sounds like some sort of proprietary ink. So for these, the principal solvents are also alcohols, but no glycol ethers are used. So essentially, one of the primary components of the Sharpie ink is alcohol. Okay, and so since one of the primary ingredients in the Sharpie ink is alcohol, well then, no surprise, if you try to use isopropyl alcohol to remove the Sharpie ink, it will remove it because specifically of this concept of like dissolves like. Where since isopropyl alcohol is similar in nature to the alcohol in the ink, then it dissolves it. So, providing a little bit more detail on this concept of, electronegativity and polarity, okay? Where the question was asked, and a great question was asked last time in terms of, well, what is specifically electronegativity, or is there a way to like measure it? Okay, so shown here is a very simplified version of a periodic table, and pretty much you have the symbols of the elements, okay, either the 1 or 2 letters, and then you have a number below it, okay. So what I've highlighted here, okay, are these are electronegativity values, okay? And these values, they are a measure. They're a measure of like how strong each element here is in its ability to pull electrons towards it, okay? Where basically the higher the number, okay, and the maximal number, well, I've highlighted or put a purple square over the most electronegative atom in the periodic table, which is fluorine. So it has a value of 4.0. And, these values are fairly arbitrary, okay? Where these were pretty much, calculated or determined by Pauling, okay? So that's why they're called Pauling electronegativity values for the elements, because this particular person, Pauling, pretty much, did the calculations or did the measurements and came up with it's essentially an arbitrary scale. Or like it's an arbitrary relative scale. But yeah, fluorine, since it's the most electronegative atom, okay, it has an electronegativity value of 4.0. And so as you can see, all the other elements, okay, the electronegativity value is less than 4, okay? but critically, or at least important to keep in mind, that oxygen and nitrogen, which are to the left of fluorine, right next to it, those have values of 3.5 and 3.0. And so oxygen, as you can see from the table, that is the second most electronegative atom in the periodic table. As in, aside from fluorine, no other atom has an electronegativity value that is higher than 3.5. And then nitrogen. Okay, nitrogen is also considered a very electronegative atom. Okay, where there's only there's only 3 atoms that are more electronegative than nitrogen, which is obviously fluorine and oxygen, and then chlorine now comes into play. Okay, where chlorine is, I guess technically speaking, according to this table, it's 0.2 stronger in electronegativity than nitrogen. But all that to say is this is how we measure or determine electronegativity, and this is the factor, or like pretty much one of the primary variables that drives polarity in a molecule. As I outlined here in the note, differences in electronegativity are a primary factor that drives polarity. As in, if you look at, let's say, going back to the water molecule, H2O, where you have oxygen, pretty much sandwiched, in the middle of 2 hydrogen atoms, So you have oxygen, which has an electronegativity value of 3.5, and then you have hydrogen here, 2.2, And so since that is a large difference in electronegativity, and oxygen is much more electronegative than hydrogen here at 2.2, then oxygen is able to, pull the electrons from the hydrogen more towards it. And that's how you get that, as we saw, that partial negative charge on the oxygen atom, and those partial positive charges on the hydrogen atoms. And it's pretty much, it's that principle that holds, throughout. In terms of differences in electronegativity, is one of the primary things that drives polarity, but there's also this aspect of the 3-dimensional orientation, which we've covered previously. So, well, pretty much, I went through the example already, where oxygen has an electronegativity of 3.5 and hydrogen of 2.2. And so yes, oxygen is able to win the battle for electrons, and so it results in this, where you have now, a partial negative charge on the oxygen atom, and you have partial positive charges, on each of the hydrogen atoms. And so that's why, that's one of the reasons why, water here is a polar molecule, where the oxygen, is pretty much pulling the electrons a little bit away from the hydrogen atoms. So, getting back to amino acids. Just 1 second. I need to take a sip of something, because I have... So, we're covering amino acids. And, well, we've covered why do we call them amino acids. They have an amino group. They have a carboxylic acid group. But then it also begs the question, understandably, of what are acids and bases? We're not going to do, at least maybe not yet, maybe sometime in the future, but we're not going to do a deep dive on acids and bases, just a broad conceptual overview of acids. So, we'll start with definitions, as in what are acids and bases. So as I outline here, technically speaking, there are at least 3 definitions of acids and bases, and this is one of them, where an acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions, H+, in solution, and a base is a substance that, when dissolved in water, increases the concentration of hydroxide ions, OH- in solution. So, the example for an acid, shown here that I pulled, straight from a textbook, which you have HCl, hydrochloric acid, and that is literally, the acid that you have in your stomach. And so when you put it in water, okay, it pretty much, the technical term that we use in chemistry is like it dissociates, okay, as in the H separates from the Cl, okay, and you get H plus and Cl minus. Oh, Ronan of Stag, welcome. Great to see you. Hope you're doing well. And thank you for stopping by in YouTube chat. But yeah, we're covering some acids and bases. So, yeah, when you put HCl, okay, in water, okay, it dissociates, and you get H plus and Cl minus, okay. And since we're increasing the concentrations of H plus, oh, hello, thank you so much for the enthusiasm, super appreciate it. So since this increases the concentration of H plus in solution, okay, this is classified as an acid, okay. And then similarly, okay, so NaOH, which is sodium hydroxide, very common base, if I remember correctly. This is, oh, well, thank you so much for the kind words, Ronan. Super, super kind and appreciated. Totally not necessary, but yeah, you can find me either on, you both now, YouTube and Twitch. And like, yeah, I'm getting back into the swing of things, of, streaming regularly, okay, where I should be streaming regularly for hopefully the foreseeable future, or at least hopefully, for a long time. And maybe somewhere down the line, totally not necessary, but maybe if I get large enough, you can super chat me. But that's a long ways down the line. So yeah, a base, okay, sodium hydroxide is a pretty standard example of a base, where I believe, okay, this is what is used in drain cleaner, like Drano, okay, where, believe it or not, okay, so many people are, understandably, have this idea that, a base, acids, are corrosive and, do damage, which is true. Or acids, dissolve things, and, are dangerous, which is true. And that, bases, most people seem to tend to think that bases are, safe, okay? But actually, bases, especially strong bases, are actually quite dangerous and can be super corrosive and do just as much, if not more damage, than acids, okay? And that's why I'm bringing it up, where sodium hydroxide, which, if I remember correctly, that is the primary ingredient in pretty much a drain cleaner, like Drano, because, like, yeah, it will dissolve things really rapidly, especially, like, yeah, when handling, like, sodium hydroxide in the lab, okay, it's highly advisable that you wear gloves, because you get it on your skin, and if you leave it there, it's going to do quite a bit of damage. Oh, well, good. I'm super glad to hear that. Where I plan to cover more and more, I plan to hopefully cover an entire textbook of biochemistry, and then from there, move on to other textbooks. And well, I'm glad to hear that you're studying microbiology. Are you, out of curiosity, are you taking it as a course or on your own? Both are equally valid. But yeah, all that to say is we've gone through this one definition of an acid, but we don't care about this definition. But it's important to at least have it in the back of your mind. Like, this is one of the 3 definitions of an acids and bases. So, moving on to the second definition of acids and bases. So, second definition is a Lewis acid, okay? And so by this definition, an acid is a substance that can accept a pair of electrons from another atom to form a new bond, and a base is a substance that can donate a pair of electrons to another atom to form a new bond, okay? And so the typical example shown here, pulled straight from a textbook, I have the textbook citation in the bottom right. Yeah, all that to say is, you pretty much have an exchange of, electron pairs, so to speak, to put it very crudely. It's a little bit more complicated than that, but pretty much, yeah. Acid and base coming together. You have these little electrons on the B there for the base. And so, in this case, the B base with its electrons, okay, it's donating a pair of electrons to the acid, and they come together to form an acid-base adduct, okay? That's it, in a nutshell. But we actually don't care about this definition either. Just learning casually on my own at the moment. Got something else going on at a more formal level in the interim. Oh, well, all the more power to you in terms of if you are learning it casually on your own. Well, that means that you are genuinely interested in it. And so, yeah, I would say keep going and keep cultivating the passion for microbiology. So, moving on to the third definition of acids and bases, okay, it's called the Bronsted-Lowry definition, after a person, well, whatever, famous scientist, where by this definition, okay, an acid is a proton donor, a base is a proton acceptor, okay, and so an acid-base reaction involves the transfer of a proton from an acid to a base to form a new acid and a new base. Okay, so again, I have the example shown here, pulled from a textbook, where you have HCl, hydrochloric acid, okay, and then you have water, okay, and so what happens is the HCl, okay, the HCl is donating a proton to the water, and so you have the H2O becomes H3O plus. And then you just are left with Cl minus, or the chloride ion. Well, thank you so much for the kind words. Super grateful. And yeah, I plan to hopefully do this for a while. And where, yeah, I'm getting back into the swing of things of streaming regularly. Where pretty much at this time, every Wednesday, I'm actually going to schedule it, in my YouTube as an event of like this time every Wednesday is a biochemistry lecture. So by this, what's happening here is the HCl, okay, it's acting as an acid by donating a proton, okay, and when it donates a proton, it's donating it to H2O, and therefore the H2O becomes H3O plus, and we call that the hydronium ion, okay? And then what's remains left is a chloride ion, okay? So the HCl is the proton donor, and the H2O in this case is the proton acceptor, okay? So that is the acid-based reaction according to the Bronsted-Lowry definition. And for this, okay, this is actually the definition that we are interested in, that we're going to essentially be working with. Because, believe it or not, acid-based reactions like this are pretty important, biologically and biochemistry speaking. Where, yeah, basically the transfer of protons and the acceptance of protons is like very common in biology and biochemistry, as we are going to see. And that's why I'm introducing it now. Not only is it important to understand, let's say, amino acids, okay, but it's also going to be important when we cover, other things in the biochemistry world. So, but what is it? What is a proton donor? And, what is, a proton acceptor? Okay, so, yeah, that's why I pose it here as what's a proton, or what's a proton donor? So, when we covered the periodic table, okay, recall from the periodic table, hydrogen has 1 proton and 1 electron, where hydrogen, that's element number 1 in the periodic table.
Welcome to Flavor Country.
Gina Jake, thank you so much for the follow, and well, great to see you again. I believe, well, yeah, I believe I know you from Discord and Instagram. But yeah, thank you so much for the follow. Super appreciated. Nice to see you. I've been well. I hope you have been doing well also. So, yeah, hydrogen from the periodic table, okay, it's number 1, okay? And as mentioned when we covered the periodic table, it's arranged, okay? It's arranged in order of protons, number of protons, okay? And since hydrogen is number 1 in the periodic table, that means it has 1 proton. And then helium, since that's number 2, that means it has 2 protons, okay? Hydrogen has 1 proton and 1 electron, as I highlight here in the text, okay? And so, what happens, okay? What happens when hydrogen loses an electron? Well, when hydrogen loses an electron, what's left is only 1 proton, okay? That's why, okay, going back to this example here, okay, HCl, okay, in this case, we call it a proton donor, okay, because, well, you have a hydrogen, okay, and you have hydrogen HCl, okay, but when the HCl, okay, is acting as an acid, and it's called hydrochloric acid, what happens is it donates a proton, okay, where, yes, you can say it's donating hydrogen, but all it's donating from the hydrogen is the proton. That's why, okay, it becomes H3O+, because the H2O has gained a proton, okay, and therefore if it's gained a proton, it's gained a positive charge. And then the chlorine, okay, the chlorine pretty much keeps the electron from, the full hydrogen, okay? You got to keep it in mind that, full hydrogen from the periodic table, it's 1 proton and 1 electron, okay? So, the proton part of hydrogen is being donated to the H2O, so it becomes H3O+. And then the electron gets left behind, okay, with the chlorine, and that's why it becomes Cl-, okay? It has kept that 1 electron, from the hydrogen, okay? So that's what we mean by proton donor. It's pretty much donating a proton in the form of, like, a hydrogen, okay? But it's, like, only a part of the hydrogen. Pretty much hydrogen is composed of just 2 things, 1 proton and 1 electron, just like I've outlined here. And so that's what we mean by basically proton donor or proton acceptor. Pretty much donating or accepting hydrogen, but not all of hydrogen, just the proton. And so, again, not super critical to, like, have, a full understanding of this concept, but pretty much just but at the end of the day, we're going to be revisiting it over and over. So, at some point, stick around long enough, it's going to be embedded in your brain pretty strongly. So, and well, yeah, I pretty much go through, what I just went through. So, yeah, just to reiterate, okay, I almost have forgotten the slide that I prepared. So yeah, in this reaction, okay, HCl is your proton donor, the acid, and H2O is your proton acceptor, okay, the base. Chlorine is much more electronegative than hydrogen, so it steals its electron, okay? So pretty much just reiterating what I just went through, okay? Where HCl is acting as the proton donor, okay, giving away, okay, that 1 part of hydrogen, which is the proton, and then the electron gets left behind. So, what are acids and bases? Okay, well, shown here are a table pulled straight from a textbook, okay, of common acids and bases. And as I mentioned, you don't really need to know these, okay? Well, at the end of the day, I'm not really going to be, like, testing or grading you on these things. But all that to say, it's not super critical to, keep these in mind, other than what I put in the purple box, which is ammonia, which is classed as a weak base, okay? And when we say weak base in this context, we mean that it's a weak proton acceptor, okay, going by the Bronsted-Lowry definition. And so, no surprise, okay, this is part of the amino group, okay? So, as we just saw in the last slide, okay, NH3, that's ammonia, okay, and it's a weak base. And so we have an NH3 here on the amino acids, okay? You have an amino group that has gained a proton because it is basic. So again, ammonia is a weak base. And then you have your carboxylic acid group, that lost a proton because it is acidic. So that's why it's here shown as COO minus as opposed to COOH. So basically, the carboxylic acid group has lost a proton because it is acidic. It is a proton donor. Okay, so, and as we're going to cover, and I think should be in the next few slides, whether the amino or carboxylic acid group is protonated or deprotonated depends on the surrounding chemical environment, as we will see next. Where they don't, the amino acids don't always, have the COO minus, or it's not always a negative charge, and it's not always a positive charge. Sometimes they're neutral. Although more often than not, as we will see, there's a reason why they are depicted this way, because pretty much, in their native environment, so to speak, you have the negative charge, as in the carboxylic acid group will have lost its proton and become COO minus, and the amino group will have gained a proton and become NH3 plus with a positive charge. So why is that? So there is this aspect of, as I mentioned in the last slide, the chemical environment. So as a note, but we're going to again be revisiting this concept multiple times, but in this little figure here, it's more or less just a graph where you have pH, pH on the x-axis, and you have concentration, or you can also reword it as like abundance, how much of the stuff that you have, and even though it looks super complex and complicated, all it's trying to show you is pretty much how the amino acid, how the, let's say, the example amino acid, this is just like some random amino acid, that's why there's an R group there, but pretty much how the amino group and the carboxylic acid group change as the pH of the environment changes. But at least the key thing for this one that I just want to point out, we're going to be seeing this multiple times, because I'm going to try and dissect it and get the message across. But at physiological pH, which is pH 7.4, which is why I put that red vertical bar there at pH 7.4, the Zwitter ionic form of amino acid predominates, where that's where you get the COO minus and the NH3 plus, and well, what do I mean by physiological pH? Well, we'll see that pretty soon. But physiological pH essentially just means the pH of the body, sort of like the pH that you have in your bloodstream. That is pH 7.4. Yeah, here that's a fantastic Beatles song. I'm gonna take a sip of something. One moment. That's why we typically show amino acids like this, but they can be in the other forms, So the other forms are in the pinkish, reddish background and the greenish, light greenish background, Whereas the pH of the surrounding environment, changes. And that, begs the question, well, what is pH, And, most people at least have some, fundamental understanding of pH, which is a measure of acidity, But it's a little bit more, slightly more complicated than that, or at least there's more detail to that, which is pH is simply a measure of the proton concentration of a solution. The more protons in solution, the more acidic, and the lower the pH, And the less protons in solution, the more basic, and the higher the pH, Okay, and so there's this formula here. This is essentially, the fundamental formula to calculate pH, where pH is equal to the minus log of H plus in those square brackets there. Those square brackets, as I put there in the note, square brackets just means concentration. That's sort of like, chemistry, whatever, symbology or symbolism for concentration, or chemistry notation for concentration. So there's the pH scale here. Most people know that goes from 0 to 14, although technically it can go lower than 0, and it can go into the negatives, and it can go higher than 14. But either way, your standard, run-of-the-mill pH scale is 0 to 14. And so you have, let's see, do they give hydrochloric acid here? They don't. But you can see, so pure water is pH 7, so neutral, or perfectly neutral, or at least in theory on paper. Okay, water is supposed to be pH 7. In reality, in the real world, it's not pH 7. It's water. Water exposed to air is technically slightly acidic. But you have also human blood and tears. Okay, so that's where the pH 7.4 comes into play. Here's where the hydrochloric acid would be, the gastric juice in the stomach. So that's about pH 2. Homemade soaps, like kind you get at a farmer's market and through friends, soaps against litmus tests. Not that I'm an expert soap maker, but I can't imagine. I shouldn't say that. I'm not sure why you would want to test your soaps with, let's say, litmus paper before packaging them. Like, I don't think it's super critical, like, unless, I don't know, there's some sort of quality control that you're looking specifically to do. But yeah, I might be a little bit ignorant on soaps. But I can't think of a particular reason as to why you'd want to test them specifically. I might have to look into that. Because now I'm curious. But I don't think there's, any particular reason as to why you'd want to test them. Your pH scale, okay, pretty much 0 to 14, okay, and well, below 7, acidic, above 7, basic, as most people know. Also, as further example as to how corrosive bases can be, it's like, well, you also have the example here of oven cleaner, okay, to clean your oven, you generally need pretty strong stuff, and so that seems to be between pH 13 and 14. And then you have household bleach, which pretty toxic and potentially dangerous stuff at pH 13. So essentially, the more protons you have in solution, the more acidic you are, and the less protons, the more basic you are. And that's pretty much what they're showing here. Of acidic solution, you got a lot of H+. A neutral solution, you got a balance between H+ and OH-. And then, a basic solution, you have, less and less H+. Okay. Gotcha. If there's some sort of like regulation or industry standard, then I understand. I thought like maybe like to test for, some sort of safety, although I guess that would be in some ways testing for safety. You can, probably the paper is the most convenient and cheapest. But you technically, you can buy pH meters for sure. Although let's say there's fancier things than, let's say, litmus paper. But litmus paper can, I imagine, do the job. But let's just say if you're willing to spend money, and whatever, you're on essentially an unlimited budget, you can buy a pH meter. That is literally like an electrode that you dip in, and it will give you like an exact pH, like to 2 decimal points, as opposed to like your standard litmus paper. You're probably gonna get just like whatever pH 1, 2, 3, 4, 5, or whatever the range is on the litmus paper. Yeah, there's multiple methods where I can show, I guess, after the lecture, or if you Google pH meter, like you will definitely get a bunch of hits of things that you can buy that will allow you to measure the pH to a higher degree of accuracy, if that's what you're looking for, and you don't mind spending quite a bit more money. So, how is the formula for pH used? Okay. Not that, at least as of right now, we're not going to be doing any real calculations, but just for informational purposes, I at least want to show how the formula would be used. Okay. So you have the formula, pH is equal to the minus log of the proton concentration. And so, yeah, I just put here a simple pH problem, as in calculate the pH of a solution with a hydrogen ion concentration, or H+, of 1 times 10 to the minus 3 molar, or capital M for molarity. That's chemistry notation, or rather chemistry terminology for like a concentration, similar to like percentage that you would, let's say, see on milk. Okay, as in 2% milk, that means it's 2% concentration of milk fat. Okay, and so all I'm saying, this M here stands for concentration, as in 1 times 10 to the minus 3 molarity. That's a concentration, just as 2% milk is a concentration of milk fat, or 3.25% milk is the concentration of milk fat in milk. It's just it's a slightly more complicated way of tracking concentration. But all it is a concentration. We call it molarity. Soap for human. I don't know for sure. I can't imagine. I don't know. I mean, given we could even go. So I would imagine, okay, just based off of like, let's say this, okay, probably I would suspect, okay, in the range of like between like 5 and like 8, or if anything even more narrower, of like 6 and like 7.5. I could be wrong. Like I'm just going by what I would think of, like would be not corrosive. And I guess obviously it would depend on like the type of soap. If you're talking about like your standard like bar of soap, like Ivory or Dove, I would imagine it's probably like, yeah, between like 5.5 and like 7.5, or like 6 and 7.5. But that's me just like giving an educated guess. Because I think pretty much outside of that range, you potentially run the risk of, like, given enough time, it would be like corrosive. So yeah, how do you use this formula? So yeah, this is just a simple pH problem, and so what you end up doing, okay, is if you just put in, you plug the number into the formula, okay, where if you put in this 1 times 10 to the minus 3, okay, into this formula, right there where the H plus is, you'll get an answer of 3. Or at least you should, if I've done my due diligence. Where the pH of this solution would be 3. If you put in 1 times 10 to the minus 3. And you can double check it on a calculator if you want to. But even though that's, in reality, that's a simple calculation, I double and triple check that. So, should be right, unless I could be totally incompetent. So, yeah, the amino acids. Okay, so a good conceptual understanding of pH is important in order to understand amino acids because, well, yeah, they're they're acids, but they're also bases. Okay, the amino group on amino acids, as we just saw and as I covered, that's basic, as in it's a proton acceptor. But pKa is also a measure of acidity. More specifically, how likely a group is to donate a proton. And so the lower the pKa, the more likely it is to donate a proton, or basically the more acidic it is. So shown here is a table, okay, pulled from the biochemistry textbook that we're following. And the table is typical pKa values of ionizable groups in proteins. Okay, so you have your terminal alpha carboxyl group. Okay, so it's an acid. Okay, and here is it in its basic form. So the typical pKa is 3.1, as in this, okay, this COOH here, okay, the carboxylic acid group, okay, it has a pKa of 3.1. That's a measure of how likely it is to donate a proton. And when I say donate a proton, pretty much lose this hydrogen, or, lose, the proton part of the hydrogen. Okay, and that's why pretty much if you go from acid to base, you see that in each case, the H is lost, or one of the H's is lost. Where here you go from carbon, oxygen, oxygen, hydrogen to carbon, oxygen, oxygen. And then the same theme, for the rest of them. And so, all that to say is going by pKa, and this is arranged by pKa. So, going by the note there, the lower the pKa, the more likely it is to donate a proton, or basically the more acidic it is. So, the terminal alpha carboxyl group, okay, the one at the top here, is way more acidic than, let's say, arginine down here with a typical pKa of 12.5, okay, where it's arranged by pKa in ascending order. So since it's in ascending order, you are going by decreasing acidity, okay, where out of all of the ones shown here, okay, this terminal alpha carboxyl group, it is the most likely to donate a proton. And therefore this, of the ones here, this is the most acidic. Okay, and then the arginine, that is the least acidic, or the least likely to donate a proton, or, give one up. And then you have all the rest in between that represent, some parts of the amino acids. You have aspartic acid and glutamic acid, okay, histidine, that's amino acid. The terminal alpha amino group, okay, that's that NH3+, okay, that has a typical pKa of 8.0, okay, and they have cysteine, that's an amino acid, tyrosine, lysine, and arginine. So, that's pretty much pKa in a nutshell. So, if the pH of the surrounding environment is higher, okay, that is more basic than the molecule group, it will lose a proton. And then conversely, if the pH of the surrounding environment is lower, okay, that is more acidic than the molecule group, it will gain a proton. Okay, so, there's, understandably, it's a little hard to keep track of and, wrap your head around it. Although, we will go through examples, and we will see. And I'll try to break it down as best I can. But all that to say, so let's say you take your terminal alpha carboxyl group, okay, that has the pKa of 3.1, as in this COOH here, this arrangement of atoms here, it has a pKa of 3.1, okay? And so, if the pH of the surrounding environment is higher, okay, that is more basic than the molecule group, it will lose a proton, okay? So, if the surrounding environment is higher if the pH of the surrounding environment is higher, so then higher than 3.1. So let's say, okay, you take this terminal alpha carboxyl group, okay, and you put it in an environment, okay, where the pH is, let's say, 6 or 7, or pretty much anything higher than 3.1. Well, that means, okay, just like I've outlined here, it will lose a proton, as in it will convert from COOH to now this COO minus form, if the pH of the surrounding environment is higher than this pKa. And then the same thing holds true, okay, for the rest of them, where for, let's say, histidine, okay, to go from the acidic form of histidine to the base form, or the acid form of histidine to the base form, okay, histidine needs to be in an environment where the pH is higher than 6, okay? So if you take this histidine and you put it in an environment where the pH is, 6.5, 7, 7.5, whatever, then you will not have the acid form of histidine, you have the base form of histidine, okay? And then conversely, okay, going back to the terminal alpha carboxyl group, okay, if you put this, okay, in an environment where the pH is less than 3.1, well, then that means that you'll be in the acid form of the terminal alpha carboxyl group. As in, if you put it in, let's say, an environment where the pH is, 2.5, whatever, or 2.9, again, anything lower than 3.1, then the acid form predominates. And again, it's the same theme throughout the rest. This is pretty much your two guiding principles here. Where, yeah, if the environment, if the pH of the surrounding environment is higher than the pKa, then it will lose a proton. And if the pH of the surrounding environment is lower, okay, then it's lower than the pKa, then it will gain a proton. So why do I cover that? Well, I cover that to hopefully, make this more understandable, okay? Going back to this figure or graph here of, like, pretty much you have the pH of the surrounding environment on the x-axis, okay? And we're seeing the changes over time of what happens to the amino group and what happens to the carboxylic acid group, okay? So as the pH of the surrounding environment increases, okay, from 2 to 4, the COOH group, terminal alpha carboxyl group, loses its proton, okay? So pretty much tracking, so you have the 3.1 pKa of the COOH here, okay? So 3.1 is, between 2 and 4. So you can see, okay, that as the pH of the surrounding environment increases and, approaches 3.1, okay, you see the pinkish reddish go down, as in you get less and less of that, okay? And then the blue starts taking over, okay, where pretty much the COOH has now been converted to COO minus, so the carboxylic acid group has lost its proton because it has transitioned from an environment where the pH of the environment is higher than 3.1, okay? And then, it goes and goes, okay? And then, now we can follow the amino group, okay? So I pulled this from the table that we just saw. The typical pKa of the terminal alpha amino group, okay, is 8.0, okay? So we're here now in the blue region, okay, where now from pH 4 up until, about pH 8, okay, the blue form predominates, okay, where the COO minus, okay, the COOH has lost its proton, okay, it's become COO minus. And now, okay, the amino group, the NH3 plus, okay, up until, okay, pH 8.0, okay, whoopsies, up until pH 8.0, okay, the blue form predominates. Okay, and then once you get higher than pH 8.0, okay, the blue starts going down, and you lose the proton on the amino group. Okay, so it becomes NH instead of NH3 plus, it becomes NH2 in the green region there, and then the green, okay, starts increasing. You can see it starts increasing. It's pretty much like a transition, like as the pH goes from 8.0 to like 8.1, well, the blue decreases and the green increases. Where pretty much you're seeing, the loss of protons over time. Like going from pH 0 to pH 3 or like 3.1, you lose the proton on the COOH. And then from pH 3.1, okay, up until about pH 8 or 8.0, and then after 8.0, you lose the proton on the NH3, okay, and that's what they're showing here, losing a proton, and then it becomes NH2, okay, and so that's why, okay, going back to this aspect of physiological pH, okay, of pH 7.4, as I mentioned, is physiological pH. And so pH 7.4, okay, is, right there between, 6 and 8. And that's why we say that COO minus and NH3 plus, that's the form that predominates at pH 7.4, which is physiological pH, the pH of the body, or what you find in your bloodstream, the pH of your blood. And so, going back to all the other amino acids, okay. So, as I make clear, since scientists are lazy, we often refer to amino acids using a 1-letter or 3-letter abbreviations. That should be not of, but or. I'm going to correct that later on. But yeah, all that to say is here are all the amino acids, all 20 of them. Yeah, 10 and 10. You have, their full name, alanine, but then you have the 3-letter abbreviations, and then you have your 1-letter abbreviations. Where the 3-letter abbreviations, most of them are intuitive, okay, where alanine gets shortened to ALA, and then gets shortened even more to A. And then arginine gets shortened to ARG, and then gets shortened even more to R. But some of them are a little bit less intuitive. That's something that I, sometimes have trouble remembering. Let's say tryptophan. Tryptophan, well, easily gets abbreviated to TRP, trip. But then the 1-letter abbreviation is W, which W doesn't appear at all in tryptophan. Since Y was taken by tyrosine. But yeah, all that to say is pretty much we try to use shorthands very often. And then I think, yeah, I think actually this is a good place to stop because I think we covered quite a bit of ground. And this starts like a whole new topic. Not a whole new, but let's say a whole new section on amino acids, as I put there in the title, linking amino acids together. We've done a pretty deep dive on the amino acids, covering the properties, how they behave in different chemical environments as the pH increases or decreases. Okay, we've covered acids and bases, or at least a primer. In a nutshell, what are acids and bases? And then yeah, I'm glad that we covered this. And yeah, we covered pH as well. And so, yeah, before we start like a whole new section on amino acids, where we start linking them together, okay, and assembling what we call a polypeptide, I think this is a good place to stop and keep this for next time. And yeah, I want to make sure that I conserve some of my slides. I think we covered like, about 20 slides today. So yeah, quite a bit of ground covered. So Let me just close my presentation. There's other stuff that I want to cover. One second. Oh yeah, and Ronin. Yeah. If you're interested in, let's say, fancy, pH readers, okay, this would be one of them. But like, yeah, as mentioned, way more expensive, in the hundreds or thousands of dollars. So just be wary or be aware. Oh, it helps if I show my screen. Yeah, these are the fancy pH meters. In the hundreds or thousands of dollars. But probably overkill for like measuring the pH of soap. Okay. So just sort of as a break, like last time, let's do some connections. Just to sort of, I guess, reset my brain. Alright, martini, teeth, humor, pendulum, steps, teabag, monkey bars, tetherball, teetotaler. I'm technically a teetotaler. Slide, boomer, desert, swings, yo-yo, teeter-totter, blues. Well, at least what stands out to me, for sure, is teeter-totter and monkey bars, swings, and slide. Yeah, almost certainly that has to be like playground equipment. Pretty straightforward for that one. The New York Times connections seems to always be, sort of like hit or miss, where sometimes it's super complicated, or at least I can't make the connections and absolutely fail. Sometimes it's super easy. Steps, teabag. I mean, yo-yo and pendulum, they like swing or go up and down, or go through some sort of repetitive motion. As well as like a tetherball, for sure. Then, well, I guess technically a tea bag goes through like a repetitive motion. At least that's the connection that I see. Like these seem connected for sure. In terms of a yo-yo, pendulum, tetherball, in terms of some sort of like a repetitive motion back and forth or up and down. Same thing with a tea bag. I'm just gonna go for it. Oh, I got it right, but for the wrong reasons. I did not make the connection of at the end of a string or a chord. Oh, my pleasure. Blues, martini, steps. I mean, I see double vowels. T for teetotaler, T for teeth, boo for boomers, but I don't see any other double vowels. I would like to think they would do something a little bit more complicated than that. Um... Um... I'm not too sure about this one. Okay, teetotaler abstains from alcohol. Pretty much like myself, or like, you know, I consume alcohol like once a year. Maybe twice at most. Teeth. Desert. Oh, okay. I think I see a connection of, okay, teetotaler, dry, desert, dry humor, even though, like, I'm a teetotaler. I have heard of a dry martini. Gonna go for that one. Okay. Somewhat straightforward. Teeth, steps, boomer, blues. I don't know what the connection is there. But since it's pretty much what's left over, I don't need to know. Oh. Well, I probably should have known that. Yeah. Baby blues, baby boomer, baby steps, baby teeth. I probably should have got that before I got described as dry. The baby blues, boomer, steps, and teeth should be way more obvious than described as dry. But whatever. This is a fairly easy one. So yeah, so I'm glad you asked. There's definitely an uptick in cases. I believe like we've seen an increase in hospitalizations that we haven't seen in like a year. We're like, yeah, definitely there's a spike. Now, in terms of like public health like measures, okay, well, unfortunately, like there hasn't been any sort of like public announcements, encouraging masking. Obviously, no mask mandates either. Like at most, there was an article today in my local news saying how they're going to be rolling out, the updated boosters for the fall winter pretty soon, that you're encouraged to get them, or at the very least, if you are in one of the high-risk groups, like the elderly, or immunocompromised, like myself, then you should get a booster. Which I got one, not that long ago. I think it was in May or June. I know I pretty much got one right before the summer, or like in the middle of summer. Thank you. I appreciate that, Ron. I hope so too. Although, unfortunately, it's not only has like the public, seem to have moved on from COVID, but even our public health agencies also appear to have moved on from COVID, at least in their mind. Obviously, it's still around and very real. Okay, another game, which is basically guessing the location and the year, which I believe this is Tony Blair. And this definitely looks like a picture from Europe. I hope the situation is, much better where you are, Ronan, than where I am. And I'm gonna put 90. Well, yeah, Tony Blair. I can't remember, but I think was in the 90s. Or early to... no. We'll go with... yeah, I think early 2000s. Go 2005. I don't think there's any really good other indicators. Yeah, I think I'm at least 6, if not 7. And if in fact, which I'm pretty sure I got like a booster in April, May, then I'm due to get one in October, November. Yeah, more and more. Oh, Jack, welcome. Great to see you. Hope you're doing well. Thank you so much for passing by. Oh yeah, that's where my intuition was going. Although I actually did not clue into the Argyle tie. Or yeah, the 5G just keeps getting better and better. I'm sure I'll be up to 6G pretty soon. I'm gonna make a guess. Oh, I should have went with my original intuition. So that was Tony Blair. Okay. Oh, never... well, I'm not going to tell you what to do, but totally not necessary to apologize. Like, at the end of the day, I'm grateful whenever you can make it. But we just finished covering the amino acids, or let's say, well, wrapping up, the chemical properties of the amino acids, and then we stopped. Which we're going to do next time is we're going to start linking the amino acids together, and how do you form the peptide bond, polypeptides, building up to the structure of proteins. So, slowly but surely, covering ground. Okay. iPhone 7. I think this is, yeah. I don't think this is the United States. There's a phone number here. I don't know what 9885025. This looks like somewhere in Europe. Oh. Asian Institute of Nephrology and South India's largest kidney institute. Okay. So iPhone 7, aren't they? I'm not an iPhone user, but I think they're on iPhone 11 or 10. I think iPhone 7, I guess, would have been like 2013, 2014. Well, great question. So polysaccharides, that's almost certainly going to be on the chapter on like carbohydrates. Let's see. And yeah, this is the textbook. Oh, no, not this one actually, not 7th edition. But I believe it's not for a few chapters. Like, so I mean, this is what we're on now. Chapter 2, we're just about to start secondary structure. So, and I know that, like, we're gonna cover DNA pretty soon, chapter, like, 3 or 4. Genes and genomes. Enzymes, catalytic strategies, right? Yeah, so chapter 11 at the very least. We don't start, doesn't seem like we start carbohydrates and saccharides. But I mean, as we're covering proteins, which I mean we'll be covering proteins consistently throughout the time. But if you have like specific questions about, because I can always, well, now that I'm able to pay attention to chat. If you have questions about, let's say, as we're covering proteins, well, how do you form a the saccharide peptide bonding and all that stuff? I can totally answer that like on the fly, or I can do like a little bit of a detour. Yeah. Hemoglobin. Yeah. So it might not be for a while, unfortunately. But maybe I can prepare some slides as just like a primer on covalent modifications of proteins, glycosylation of proteins is, or glycosylation in general is a little bit of a specialty of mine. So, okay. I don't have to, but I have to assume, given this sign, that the Asian Institute for Nephrology and Urology, okay, it's not necessary, but if you want to keep it on, I'd appreciate that. Since they say this is South India's largest kidney institute, like I have to assume this is in South India. I'm surprised there's this much English. Okay. Let's see if I can find like an exact location. Like license plates don't seem to be of much help. Well, the more you know. I definitely do not know that. Okay. Whatever. I'm just gonna go with whatever. About as South India as you can get. Whatever. Somewhere here as like a middle ground. Now, I believe they're on iPhone 11. Okay, and I don't think they come out with a new iPhone, or I don't think they increase the number every year, given that, well, basically, I don't think that if in fact we're on iPhone 11, okay, I don't think the iPhone 7 was 4 years ago, 2020, but I could be totally off, because I don't really follow Apple product launches, or Apple products in general, but assuming like every 2 years, okay, every 2 years, so this is 4 iPhones ago, so like 8 years ago. I'll go like 2017. Cause yeah, I think, didn't they like skip like iPhone 10 or just go for... No, I'll go with my original intuition. 2015. I don't think I'm gonna get anything else in terms of location other than South India. Alright. Gotta commit to something. Okay. I guess that's technically South India, if I, like, draw right through. I'll take it. 8,700. I don't know what this is. Okay, let's try and narrow down a year. Okay, these cars, to me... these cars, to me, seem like 60s, 70s? I think more 60s. I'll go with, like, 68. Location... I don't think the license plates give me any indication. I don't know if this F. Like this sign here, like, you know, my brain, since it's so elementary, like, I just think, is this some way of, like, whatever, yeah, the only thing that comes to mind is, like, Sicily, just because it's similarly spelt. I have no idea if there's any connection at all. I'm just going by O, since it seems to have letters in common with the word Sicily. Therefore, it must be related to that. Yeah, I don't know how I'm supposed to determine location here. You have what looks like taped windows. Nothing about the architecture says anything to me at all. Yeah, well, I'm just gonna go. I'm gonna go with just like my most basic analysis. I mean, I agree, but like I got nothing else to go on. And since that, you know, I'm gonna go by my own answers. I'm gonna try not to use any information from chat. And I can't even, like, locate Sicily in Italy. Oh, there it is. Okay, do I want to commit to the 60s? I think for sure 60s and 70s. Well, I mean, yeah, I should keep you off screen to, you know, be whatever, super honorable. We'll split the different. We'll go, you know, whether it's 60s or 70s, we'll go just right at 1970. Okay. I was way off. Well, you were right. Your intuitions were right, Jack, in terms of France and French. But either way, I'm glad I got the year. Or I was close to the year. I think I should have went. I think my original intuition was 1968. But whatever, good enough. I'll take it given the limited information. Okay. Uh... Okay, these cameras here, I think. I want to say, like... 70s, 80s? Location-wise... I can't recognize this military uniform. At all. And I don't know where there would be whatever primates just roaming around. I mean, going by like the background of the people, I want to say somewhere in Europe. But then I don't know where in Europe there would be. Oh yeah, if in fact it is, which, you know, I believe you, I don't know where they would be freely roaming around like that. Let's see, any identifiers on the uniforms? Yeah, I can't. All right, we'll commit to a year. Judging by, at least for me, the cameras, you know, these seem like not the worst cameras. The clothing, I'll go with the good old Back to the Future, 1955. Okay, this person's headwear seems to be checkered, at least to my eye. The only thing that comes to mind that's like whatever checkered is like Croatia. But again, that's just like the most loosest of connections. Well, I mean, Croatia is near water. It's definitely split Croatia. 100%. But like that background, oh yeah, definitely near water. We'll go for it. Oh, I was only 1 year off, so I'll take that. I was way off in the location. That's south of Spain. Princess Anne feeding nuts to a Barbary macaque in Gibraltar. Legend says that as long as the macaques remain on the rock, Gibraltar will remain under British control, prompting Winston Churchill to sustain their population. Okay. Well, I'll take it. Good enough for me. I got the year pretty well. And given that I had no idea where the location was, it's good enough for me. Okay, West End Florist. Okay, this, to me, at least car-wise, says 40s? No, No, I think 50s, 60s. My references for cars, at least old cars, is always like Back to the Future. And so these look like more modern than Back to the Future. So after 1955. You have a Pepsi. Okay. You have something village. This looks like, I read it as Fermanson Village. Not that I have any idea where that would be. We do magic with flowers. Use friendship. I mean, I want to say New York. Isn't there like whatever? I don't know. A West End in, I mean, there's a West End anywhere, but I don't know. Just that terminology makes me think somewhere in New York. There's English. I mean, this looks like, you know, a major city. There's large buildings in the background. So a developing city. Let's see if I can make out some of the other stuff in the background. You have Eddie's Lunch. Oh, snow. Okay, so it's snow emergency route. Okay, so like definitely no, almost certainly nowhere in the south. Okay, so like northeast is definitely making me think more and more New York. If they have to have a snow emergency route. With like a major city, like yeah, definitely. Kindly wait till I make my bad guess. Yeah, no, I just gotta go with my gut. Whatever. Well, since it says West End Flowers, doesn't it not say that? Yeah, West End Florist. So we have the Upper East Side. We have the Upper West Side. But not the West End. But whatever. Oh, West End Avenue. I might have maybe gotten lucky. I'm assuming West End Florist is on West End Avenue. Although West End Avenue is pretty... whatever. Pretty long. Okay. The year... You have these vans. And this little bus here. Yeah, I want to say like 1965. You got 7 Up here. Have a Pepsi. We'll just go for it. Okay, I'll take it. I was quite a bit off of location. Yeah, Baltimore. I don't know how I don't know what the giveaway is for Baltimore. I thought I was, yeah, I thought I was really good with the West End Avenue. But what's this? What street is this? Is this also West End? West Baltimore Street. Okay. Well, whatever. I'm pretty happy. I got the year pretty well. I think I'm just under, yeah, just under 40,000. Not too bad. Not too shabby. I don't know how I was supposed to get Baltimore from that. But obviously, I'm Canadian. And yeah, this connections was pretty
easy.
Got lucky with that. Okay, so, well, my original plan was to cover the paper that I wanted to cover this past weekend. But I also want to do it justice. And so I don't think I'm going to cover the paper. I'm going to cover other things, other science news. Where, yeah, the paper that I want to cover was... I'm going to save it for this weekend. But yeah, it's the one that I mentioned previously. Which was this one, yeah. The catalytic antibodies. Really good paper, really cool paper. Probably gonna save it for Saturday, because I don't think I can do it justice in, let's say, you know, the hour left that I plan to stream. So, gonna cover other science news. Which is this. Which, a new study just published, I believe, which is this one, publication date. Accepted June 2024. Where is the PDF? Yeah, published. So yeah, it's published last week, like literally a week ago. August 21st. Of, yeah, psilocybin. Or it looks like it's a comparative oral monotherapy of psilocybin, lysergic acid diethylamide, which is LSD. 3,4-methylene dioxymethamphetamine, which I believe, memory serves me correctly, that's essentially MDMA. Yeah. Ayahuasca, escitalopram. Okay. So yeah, psilocybin may be as effective as common antidepressant in treating depression. Which, no, psychedelics are getting a lot of press these days, a lot of coverage, because, yeah, there's more and more published studies coming out showing quite, well, there's a mix of studies, but there's quite a bit of them showing positive effects, which I've covered psychedelic research before. So, psychedelics are substances that may be beneficial in treating mental illness. Research is ongoing about the effectiveness of using psychedelics such as psilocybin and how they compare to more traditional treatment options. Evidence from a recent review suggests that the psychedelic psilocybin at high doses was slightly more effective at treating depression than the common antidepressant escitalopram, which I think is Celexa, if memory serves me correctly, or brand name Celexa. Or yeah, Lexapro. I was wrong. Ciprolex. Maybe I have that in mind instead. Depression is a widespread mental illness, impacting about 280 million people worldwide. Researchers are interested in expanding treatment options and finding the most effective medications. Using psychedelics to treat depression is one area of ongoing research. A review and meta-analysis published in the British Medical Journal compared the effectiveness of psychedelics to escitalopram. The results of the review indicate that high doses of psilocybin were minimally more effective than escitalopram in relieving depressive symptoms and slightly more effective than the placebo results in escitalopram trials. The results suggest that psilocybin may be comparable to current antidepressant treatment. So, how do psychedelics stack up to other treatments for depression? Psychedelics are psychoactive substances that have the potential to treat severe mental illnesses like depression and post-traumatic stress disorder, PTSD. Common examples of psychedelics include psilocybin, LSD, and MDMA. While psychedelics have shown promise in the treatment of depression, it can be challenging to do blinded studies because of the subjective effects of psychedelics. Thus, there can be differing placebo effects and possible bias, which again, this is a common theme, or whatever. This is a recurring problem when it comes to not only psychedelic research, but also research with just about any psychoactive substance, including research on cannabis and cannabinoids. Like how do you come up with an appropriate placebo to a psychoactive substance, where most people in like let's say in the studies for MDMA or pick your psychedelic, they will typically almost certainly clue in pretty quickly that they are not receiving the psychoactive substance or not receiving MDMA, especially in some of the studies when they're doing prolonged multiple sessions, or like they're doing sessions for hours at a time. I believe there was this one study. Let's see. I have a decent amount of psychedelic research. Yeah, like this one. This one was a pretty significant study. Where they were doing, if I remember correctly, pretty intensive sessions. Although, yeah, well, since I highlighted it, they do assess whether some of them actually know that they're receiving placebo, and like, yeah, some of them seems to be, there's like a mix of like, some people are able to recognize that they are receiving placebo, and then there's some that are like receiving MDMA and they think they're receiving placebo. So there's something, at least in my mind, there's something interesting going on there. Of like they're not. Some people are not even detecting that they're getting MDMA. But yeah, well, I'm not gonna re-dissect this study because I've already done that. But like, yeah, that's a common problem or challenge when it comes to research on psychoactive substances. So how do you come up with an appropriate placebo? So the researchers of the current review wanted to compare monotherapy use of psychedelics with escitalopram, a common medication used to treat depression, to help get over some of the problems with the reduced placebo effects of psychedelic trials. The review authors made sure to distinguish between the placebo response in psychedelic studies and the placebo response in antidepressant studies. This review and Bayesian network meta-analysis included randomized controlled trials with adult participants who had clinically diagnosed depression. For all the data, they focused on changes in depressive symptoms as the primary outcome. Altogether, they were able to include data from 19 trials, 811 participants in psychedelic trials, and about 2,000 participants in escitalopram trials. So 20 trials, 80 participants. So there's about 40 participants per trial on average, give or take. Whatever, 41, 42. Based on their synthesis of the data, researchers did find that the placebo effect in psychedelic trials was lower than the placebo effect in escitalopram trials. Compared to the placebo results of escitalopram trials, high-dose psilocybin was slightly more effective. The researchers typically defined high doses of psilocybin as 20 milligrams or more. In addition, high-dose psilocybin was also slightly more effective than escitalopram. David Merrill, board-certified geriatric psychiatrist at Providence St. John's Health Center in Santa Monica, California, and Singleton Endowed Chair in Integrative Brain Health, who was not involved in the study, noted the following about the review's findings. This study used meta-analysis techniques to compare the effectiveness of psychedelics and escitalopram or Lexapro for depressive symptoms. It's notable that only high-dose psilocybin showed greater effectiveness than escitalopram. High-dose psilocybin shows promise as a fast-acting, short-term treatment for depression. This is in comparison to antidepressants, which take weeks, if not months, to kick in and only continue to work with continued use, he told Medical News Today. Though not addressed in this study, the clinical consensus is that benefits of high-dose psilocybin can last for months and potentially years after the acute episode of treatments. At times, even only one treatment session is needed for otherwise chronic intractable depression. This is part of why psychedelic-assisted psychotherapy under safe, controlled professional settings is gathering such momentum and enthusiasm in the field of psychology and psychiatry, he added. This review does have limitations. First, it's essential to acknowledge that any study included in the review had limitations. For example, researchers acknowledge that the effects of psychedelics may be overestimated compared to internal trial placebos, which is why researchers chose to look at how psychedelics compare to antidepressant placebo effects and low-dose psychedelics. They also acknowledge that participants receiving psilocybin were often also receiving psychotherapy or psychological support, which could have impacted the results. The researchers also only focused on acute effects, so future research will need to evaluate long-term effects of all related medications. Researchers chose to include a broad range of depression types and included studies with participants who had terminal illnesses or life-threatening diagnoses and depressive symptoms, alongside participants who had PTSD. Most participants in trials using MDMA and had PTSD, while most participants in escitalopram trials had major depressive disorder. Since the two conditions are different, the results may not necessarily be translated. The review also included only a small number of trials. The researchers were also limited by choosing to make comparisons to extremely low psychedelics, which is not a true placebo. The results may also have been affected by the struggles of direct and indirect evidence and direct evidence biases, which could have overestimated the effects of high-dose psilocybin compared to other treatments. The inclusion and exclusion parameters also limited the researchers, so future research could include different parameters and inclusion criteria. Finally, the researchers acknowledged that their meta-analysis may not have enough statistical power to identify publication bias. Researchers also recognized that most of the certainty of evidence for treatment comparisons was moderate or low. Bob Marley, welcome. Hello, how are you? I hope you're doing well. Yeah, I imagine you're about to start grad studies or graduate school soon, if not already. Or at least I know in my area, universities are like, well, how about either start it now or next week? Standardization in psychedelic treatment. The study authors suggest that improving blinding methods and having more standardized psychotherapies could help increase understanding of the effectiveness of psychedelics. Matthew Johnson, PhD, senior researcher at the Shepard Pratt Center of Excellence for Psilocybin Research and Treatment, who was not involved in the study, was skeptical about the review's findings and noted the following to Medical News Today. End of September. Interesting. Well, I guess I assume, or maybe your school terms are different, in the UK. But at least ours are like, they're 12 weeks, or whatever, around 12 weeks, and it goes pretty much, 3 months. September, October, November, basically. So the study authors suggest that improving blinding methods, and I guess I assume you're also still on vacation, which I hope you're enjoying. Get the last bit of enjoyment in your vacation before, grad studies start, which, depending, I guess, on your field and how your, department works, grad studies might be more intensive or less intensive than undergraduate, or more enjoyable or less enjoyable than undergraduate, where it's like, like what I did enjoy about grad school is like the greater autonomy, and obviously, I had a little bit more control over what I can do in terms of like guiding my own research. And while obviously it's different in terms of I'm not just assimilating information, like I'm trying to like gather and provide more knowledge and information and generate my own data, as opposed to undergrad. You're just like stuffing a bunch of stuff in your brain. And so like, yeah, I liked grad school for being able to do research and the more independence. But then what I didn't like as much, although not a problem for me, is like, yeah, it's a little bit less structured in terms of like, well, yeah, you're not just given material to like study and just spit out during an exam. Although maybe in your grad studies that'll be a part of it. I don't know. But all that to say, like, well, I enjoyed both, just like for different reasons. The study authors, and also I'm curious if well, I think you maybe have mentioned it before, which I apologize if I don't remember. But like, have you already like fleshed out like your research question, or like what specifically you want to like research? Or let's say, assuming you're doing a thesis-based, master's degree, do you know what your thesis will be, or like, in what direction you want to go? Dr. Johnson, the next bit needs to remember the history of murder research. He sounds like a Luddite trying to find. Yeah. Well, that's how it is with some researchers. But yeah, a major reason for my lack of confidence in this particular method is that the various studies differ too widely, including the population studied and the disorder treated, in order to directly compare them in such a way. Well, I mean, not that I'm an expert, but by my estimation, okay, the research on psychedelics is in its infancy, okay, where we don't have like hundreds or thousands. We definitely do not have hundreds or thousands of good quality, high quality, rigorous studies on psychedelics. When conducting aggregate analyses, such as meta-analysis or the network analysis conducted here, it is important to make sure that the studies aggregated are similar enough to each other to make sense. Otherwise, such techniques can lead one to think they are getting a valid answer, but you are really basing it off an apples to oranges comparison, he explained. Yeah, standard stuff. I would say the same thing about, cannabis or cannabinoid research. Like, in my mind, that's still in its infancy. Yeah, exactly. Since, there are, unfortunately, regulatory and legal issues when it comes to studying cannabis and, psychedelics and other psychoactive substances, then it's like, yeah, we have all these unanswered questions. Well, I mean, that's a valid question. Major depressive disorder and PTSD, like, I imagine, I don't know for sure, but I imagine they go like hand in hand, or like they're comorbidities. I covered this study here, which is a cool study of MDMA assisted therapy for moderate to severe PTSD, where this was like pretty not groundbreaking. Well, I guess, yeah, in some sense groundbreaking, in terms of like what they found of like the MDMA was like, at least based off of their analysis and their research, like far and away the best in terms of treating severe PTSD, which essentially, at least as of right now, as far as I can tell, and based off what they say in this own study, of like there's essentially no good or no real significantly effective treatment for severe PTSD. Okay. And at least based off of this study, MDMA was like outperforming, what they currently have as, standard of care or standard practice. And well, yeah, as they say, recurrent exposure trauma and comorbidities such as mood disorders, yeah, so it would not be surprising to me that, major depressive disorder and PTSD go hand in hand. I'm not sure whether to write the thesis on a similar topic to my undergrad thesis, which I'm working on publishing with a professor, or on something a bit different. Yeah, fair enough. These are difficult questions to, well, what I would say, if my uh, if my advice or opinion is worth anything, take it with a grain of salt. But and assuming your PI or the professor you're working with that's guiding you or mentoring you allows it, I would say do what you are genuinely interested in, where it's like, you're going to be steeped in like this particular topic for whatever 1 year, 2 years, however long your master's is, 3 years, I guess, potentially. So make sure if you're able to like choose something that you would enjoy immersing yourself in and like diving into the details. MDMA was created for therapy. It became a club drug after the government put the kibosh on research originally. I'm gonna have to look into my history of MDMA because I definitely did not know that. Despite the limitations of this review, the findings do potentially point to expanding treatment options for people with depression. This allows doctors and people with depression to choose from more therapies to find what works for the individual. Based on this study, high-dose psilocybin appeared to be similar to the effects of antidepressants in treating major depressive disorder. Thus, the researchers recommend that psilocybin should likely be used alongside psychotherapeutic support. These findings give hope to those with depression, especially those who find antidepressants to be ineffective or intolerable due to side effects. While there are always potential risks of using drugs to treat health conditions, this review shows that, with the proper mindset and treatment setting, high-dose psychedelics can be used safely and effectively to treat depression, with results on par or better than seen with antidepressant medications. Many in the field are working diligently to build a renewed evidence base to allow for the legalization and regulated approval of psilocybin and other psychedelic therapies for depression, PTSD, addiction, and other health conditions, Merrill noted. And that's the end of the article summary, which I think I have a decent amount of research on psilocybin, I believe. Which is this one. I remember... I don't think I've covered this one on stream, at least not in detail. I think I've only alluded to it. But yeah, this increased global integration in the brain after psilocybin therapy for depression. And yes, I think I've covered this one as well. Psilocybin with psychological support for treatment-resistant depression, an open-label feasibility study. Yeah, whether I want to kind of start specializing already or whether I want to be more open. Yeah, that's fair. Like, there's definitely something to be said for exploring. That's why I sort of put the emphasis of, like, make sure, or at least I would make sure that, you choose a thesis topic that you feel like you can immerse yourself in, and sort of, like, get lost in. And so, yeah, I think there's something to be said for, like, exploring a bunch of things, and then as you explore, like, narrow it down and say, oh, this is the avenue of research that whatever I'm passionate about or I can see myself like pursuing. MDMA was first synthesized in 1912 by Merck chemist Anton Kolisch, or I'm sure I'm mispronouncing that. At the time, Merck was interested in developing substances that stopped abnormal bleeding. It was then put on a shelf by Merck for 15 years until it was attempted to be used for heart-related mood disorders. Interesting. I don't know that the classification of heart-related mood disorders still exists. But yeah, I think I have a decent amount of research on psilocybin. Psilocybin therapy for females with anorexia nervosa, a phase 1 open-label feeling. It's interesting. Using the word females in, one might... You can hypothetically think that they're referring to, like, female mice, not necessarily female humans. But yeah, I'm almost 100% certain I haven't covered this one. But either way, psilocybin psychedelic research. Yes, there is some news. It's just a matter of, like, as in, I think I can make them return soon. In like, let's just say my goal is ideally end of year to like New Year, or maybe I'll make that my New Year's resolution, so to speak, of like get the gym. As in like, I have a location. At least I'm pretty sure I have a location. Or let's say I'm highly confident I have a location. In fact, it might be the exact same location that I originally did my gym streams. I believe it's just under like new ownership or new management now. It's just a matter of like making the right connections and all that stuff. So all that to say, I'm reasonably confident that I can get them to return either end of year or in the new year. But I don't want to make any promises. Well, let's see if we could take a closer look. But I'm still working out. In fact, we'll actually have a little bit of an update on, let's say, on the topic of health and fitness research that like I've covered, okay, and how I integrate it in my own life, okay, and maybe seeing the effects. But I'm just one data point, okay. But I have started incorporating, so I've covered this research before, that, technically not relevant to me, as in this is a study that I covered on stream, of, cocoa flavanols improve peak VO2 and exercise capacity, but in healthy elderly people, okay? So even though I'm not getting any younger, I'm pretty sure I don't fall in the category of elderly, at least not yet. Maybe cognitively, I don't know. But I believe their age range was like 65 plus or 55 plus. 55 plus. 55 to 79. So I'm definitely quite a bit outside that age category. But I bring this up because, I make a lot of smoothies because I have a high quality blender. And like I started adding cocoa to my, in addition to adding cocoa, I've also added I also started adding cranberries. Both cranberry juice and cranberries to my smoothies. Okay, so these two ingredients. Okay, and well, this is more. I fall more in line, although I'm not like I'm not a trained runner. Okay, and let's say given the times that they record here in this study population of like they selectively chose like pretty highly trained athletes or athletic runners, where like they can do like 5 kilometers in like under 20 minutes. I can do like 5K in like 25, or if I really push it, maybe like 23 minutes. So like, but all that to say, I think I'm closer to this study population than I am to this study population. But either way, I started adding cranberries and cranberry juice and cocoa powder to my smoothies. And like, again, this is just my subjective experience, and I'm just one data point. But like, I feel like my cardio has like significantly improved. It could have just have naturally significantly improved, just like over time, since I'm always looking to improve. Just like my handstands have improved, and like I feel like I've essentially mastered them now. But it could just be coincidence. But like, it seems, again, by my estimation, adding the cocoa powder and cranberries to my smoothies and consuming it on a daily basis has like appears to have, at least again in my opinion, has dramatically like increased my cardiovascular capacity. Of like, sometimes it just feels like I can like run forever. I'm like, I just have to stop just because like I don't have 2 hours to kill like on a treadmill. I'm not easy streamable, rowing. I would not recommend that you stream that. So I used to have a Ninja blender, okay? But no, I've since upgraded, okay? I have upgraded, okay, to one of these. A Vitamix. And already Vitamixes are expensive. But even like the base model is expensive. But even I got whatever, I guess, whatever, the Rolls Royce of blenders, so to speak. I got one of these, their Ascent series, okay, which these are like, you know, hundreds of dollars. So I got a reconditioned or refurbished one, and I got it when it was on sale. So this was back in November, so I got it during whatever Black Friday. So I believe I got it was exactly the A3500, this one. So this is 700 Canadian. Okay. But I got one that, again, was like refurbished. And it was on sale during Black Friday. So I got it for like, you know, let's say, I can't remember. It was about $150, $200 less than this. Still, well, one of the most expensive things that I've ever purchased as an individual thing. I don't usually, and well, one of the reasons why I got it, you know, so like I said, I got it back in November, okay? And that was right around the time that I got that new job that lasted 5 days. Like, one of the reasons why I bought it is because, it was on sale, and a little bit of like, you know, a gift to myself for landing a new job, although premature in hindsight, because that job only lasted 5 days. But it has been a worthy investment of like this blends much better than a Ninja blender. I was fine with the Ninja blender. Like, it did its job. I had no real complaints. But this is like really a step above in terms of like blending power and capabilities, and like smoothness and texture. I didn't think it would make that much of a difference, but it does. Yeah, I believe I was, you know, let's just say, if I were to ballpark it, I have like an 80% success rate of handstands. That's, you know, ever increasing. I hope to get it up to like, you know, 100%. But like, yeah, I think I'm effectively there. So yeah, so this study, okay, in my mind, well, in my mind, it's worth. I mean, there are other benefits to including cranberries. You know, they're pretty rich in antioxidants, and there's other data showing, let's say, even in like the muscular development realm. Okay, there may be some benefits, although maybe, you know, marginal. You know, again, like, well, one, including cranberries, it's just like it's an extra serving of fruit, right? It's just another thing that I add into my blender. So it's like not really any extra work. And like, so in this study, which was published like fairly recently, like in this, I think like in the past few months. But yeah, this was cranberry supplementation. So, and they chose 14 trained runners. Okay. And it was like, yeah, cranberry supplementation over 28 days. And it improved aerobic performance during the 1,500 meter time trial, and they also did a 4,000 meter time trial. I might have missed it. You should look into use of gallon. I don't think I've ever heard of gallon. No idea what that is. Spice. Looks like ginger to me. But yeah, going back, so just to, I guess, quickly wrap up the study. I mean, we can pretty much go over, well, didn't go over the abstract. But yeah, our results suggest that cranberry supplementation may have ergogenic effects as it improved physiological markers of performance during short and long distance running. And so, like, well, again, in this study population, okay, like, these trained runners appear to get performance benefits. Okay, and I don't think I'm a trained runner. I'm like, trained runner adjacent. Okay. And so if these trained runners saw a benefit, okay, although again in this study it was a mild to modest benefit, and so maybe the effects were amplified in, let's say, a casual runner like myself, or like semi to moderately trained runner. But yeah, again, just going by my subjective experience, I haven't tracked any biomarkers. The only marker that I track is my resting heart rate. Okay, and my resting heart rate has always been, not always, but let's say since I've been training for the past 15-20 years, I've always had a low resting heart rate because whatever, I'm pretty decently fit. So, but my resting heart rate hasn't really changed. But I feel like my cardiovascular capacity has significantly improved. Maybe I'm just training better. That's possible. Let me just catch up. I feel the more fruit you mix into a shake, the worse it. So, the trick is, at least for me, let's just say, given my medical history, okay, and the types of medical tests that I'm subjected to, where I very often have to drink something awful before an MRI or a CT scan. I'm used to drinking stuff that tastes bad, and so bad tasting stuff doesn't really bother me. Although I don't think my shakes taste bad. For me, adding the cranberry juice and adding the cocoa powder to me provides enough taste. It's not super sweet. It's I guess a bittersweet, so to speak. And thank you for the nutritional breakdown. I'm gonna have to go through that in a moment. And if you're going running, again, I don't know how long you've been running for, but let's just say if you're starting to get into running, I would encourage you to take it slow and pace yourself. My resting heart rate is, as of now, actually, in the mid to low 40s, and then every once in a while it's high 30s. Because I track my resting heart rate as a function of let's say heart health, and what and it's so I'm gonna make a prediction now, but I think resting heart rate is going to become one of the more accessible biomarkers for health. There's a reason why I track my resting heart rate. Because I have research on resting heart rate. As a resting heart rate, as an indicator for, cardiovascular disease, all-cause mortality. As in, resting heart rate, temporal changes in resting heart rate, and overall all-cause specific mortality, where, again, assuming you don't have bradycardia, which is a low resting heart rate naturally, as opposed to tachycardia. Okay, but let's just say if you have bradycardia as a result of exercise and being highly trained, that's generally a good thing, or pretty much almost universally a good thing. Resting heart rate and changes in resting heart rate over a decade are associated with mortality risk, including from causes other than cardiovascular disease, such as breast, colorectal, lung cancer, blah, blah, blah. Monitoring of resting heart rate may have utility in identifying individuals at higher mortality risk. 49 is good. You're younger than me. But either way, your average resting heart rate, okay, even for those who are, recreational exercises, will be, in the 60 to 90, 60 to 100. And you generally do have to go a little bit of above and beyond to get your resting heart rate like lower. And another reason why I track my resting heart rate is because, it's, let's say, it's correlated, okay? It's not directly correlated, but it's decently correlated to a VO2 max, where to actually get, which is, a true measure of, your cardiovascular capacity or aerobic capacity. But measuring your VO2 max is, intensive, and, you got to go out of your way, and, you need special instrumentation, you got to go to a facility, and all that stuff. As opposed to like measuring your resting heart rate, I've kept my old Samsung phone that allows you to measure your resting heart rate through just like your finger. And yeah, again, there's another reason why I indirectly track my VO2 max through resting heart rate. I mean, age is a factor for sure. Like, you're young. And as far as I can tell, like, you're overall healthy. And so that will be a part of it. Like, unless, okay, well, you've been checked out by a doctor. But, like, yeah, you might just have naturally occurring bradycardia, or bradycardia, however it's pronounced. But even then, 49 is definitely very good. Assuming it's the results of an overall healthy and active lifestyle, which I would venture it is almost certainly, given what I know about you and what you shared. But yeah, all that to say is adding the cranberries, okay, and some cocoa powder to my smoothies. Again, appears to have subjectively paid off. And I've been quite pleased, and so I'm going to continue to do it. Where now, like, now I can, so before I would run like, 10 kilometers, or like between 8 to 10 kilometers, and like, I would like feel tired like afterwards, or like I would feel drained if I like had a session of like 10 kilometers. Now it's like I do 10 kilometers and like I have to stop there just because, like, yeah, well, I'm just like, I'm not wasting time, but I have other things to do with my day than just like run and run and run. Well then, like, almost for sure, I will bet everything that I have that your lowered heart rate, okay, is the result of you being active and overall healthy, which is like, it's good that you're tracking it. That's great. Let me catch up with the nutritional information. I'm not even sure if I can get, I don't even know where I would get Gal on Gal, unless you can order it off Amazon. Even then, I'd be a little bit suspect. Quercetin, catechol. I'll look into it for sure. Okay, yeah, there's definitely Asian stores around me. I'll look in. Although, well, even though I'm not super concerned with the taste of my smoothies, if in fact it is like ginger, or like more intense than ginger, like even though like I'm half Chinese, I hate ginger. I can't stand ginger. But like, yeah, I would encourage you, if you want to, well, let's just say, the cocoa powder is like not dirt cheap, or at least a high quality one. Okay. I buy, what is it, like 300 grams? I mean, it's not super expensive either. But like, yeah, if you just want to try supplementing with cranberries, I don't know if you make smoothies, but like, yeah, I would encourage you to experiment and give it a try. Assuming you're not allergic to cranberries, assuming you're not allergic to cocoa or cocoa extract. Like, yeah, I only started experimenting with it because, like, yeah, it's whatever. It's just a couple extra things to buy at the grocery store, and a couple extra things to add to my smoothies that I make pretty much on a daily basis. And it's paid off pretty nicely, I feel. Does not taste like ginger. It is earthier with more of a bite. Maybe I'll give it a try. Okay, let's see if we can do a little bit of a... no, that, I put that in my protein shake. Although I could, it's just like, you know, since my smoothies, like, are thick, okay, and, like, you know, it's, the only reason why I don't do it is because, like, you know, let's just say, to use the chemistry terms, or biochemistry terms, during the preparation of my smoothie and, like, transfer from, like, you know, whatever, the container of the blender into the cup and me drinking it, there's sample loss, okay? As in, I lose parts of my smoothie, you know, during the blending process. I lose parts of my smoothie when I pour it into my large cup. And then I lose some of it as I'm drinking it, okay? So to ensure that, you know, when I add my 5 grams of creatine, that I'm consuming, you know, the maximal amount that I can of the 5 grams, I add it to my protein shake, and not my smoothie. But that's just me being, like, really, you know, whatever. Not OCD, but whatever. Super obsessive, I guess. Those clear ones, oh, I think, like, is Body Armor one of them? But either way, like, the ones that taste like fruit juices, I think. At the end of the day, creatine is not soluble, is not water soluble. Or at least the solubility is low. It does not dissolve in water that well. It's like less than a gram. Yeah, 13.3 grams per liter. Which is not a lot. As opposed to, let's say, if you compare it to, like, table salt. Okay. You have 360 grams per liter. As in, like, if I wanted, okay, going by this, if I wanted to make sure that, you know, my 5 grams of creatine is, you know, dissolved in water, I need to dissolve it in, like, you know, I need to take my 5 grams and add it to, like, you know, 600, 700 milliliters of water, which is, and this is at 18 degrees Celsius, so even then it'll be a little bit different. But all that to say, basically, when you dissolve creatine in water or juice, you generally want to drink it, like, right away, or, like, don't let it sit there, because your creatine is just going to slowly settle to the bottom of the glass. Yeah, okay, yeah, that's fair. I mean, if that, you know, at the end of the day, whatever works. Yeah, probably. Definitely, yeah, not the body. So all that to say, it's like, well, buying this expensive blender has been a worthy investment. Adding cranberries and cocoa to my smoothies has also been a worthy investment in my aerobic capacity. So, you know, whether you want the blender, whether, I don't blame anybody for not wanting to spend that much money on a blender. I just spent that much because, like, well, yeah, I use one day in and day out, like, pretty much every single day. So let's see if we can do a cursory scanning of this research article of comparing psilocybin, LSD, MDMA, ayahuasca, escitalopram. Common psychedelics belong to two classes. Classic psychedelics such as psilocybin, lysergic acid diethylamide known as LSD, and ayahuasca, and entactogens such as MDMA. Several randomized controlled trials have shown efficacy of psychedelics for people with clinical depression. You're not wrong. Like, I consume most, like, I mean, I have, okay, this large cup is what I put my smoothies in. This holds, like, pretty much a liter. Where, I mean, it's much easier on my digestive system. It's much easier in terms of, like, prep and efficiency. Like, given what I add to my shakes, or what I make my smoothies out of, I just don't have, I wouldn't want to spend that much time just, like, chewing that amount of, like, fruits and vegetables, of, like, kale, spinach, strawberries, blueberries, raspberries, mango, and then the cranberries, and then hemp seeds. It's just an efficient way to, like, get in a bunch of nutrition in concentrated format that will not absolutely ruin my digestive system. The proposed mechanism of its fast and persistent antidepressant effects is to promote structural and functional neuroplasticity through the activation of intracellular 5-HT2A receptors in the cortical neurons. Well, I mean, it's tasteless in my smoothies when it's all, like, blended up. Additionally, the increased neuroplasticity was associated with psychedelics' high affinity directly binding to brain-derived neurotrophic factor receptor, TRKB, indicating a dissociation between the hallucinogenic and plasticity-promoting effects of psychedelics. A meta-analysis published in 2023 reported that the standardized mean difference of psychedelics for depression reduction ranged from 1.37 to 3.12, which are considered large effect sizes. Notably, the standard mean difference of antidepressant trials is approximately 0.3, a small effect size. So they're already alluding to the fact that, at least so far, based off of the research so far, that psychedelics appear to outperform, standard antidepressants. Although modern randomized controlled trials involving psychedelics usually use a double-blinded design, the subjective effects of these substances can compromise blinding. Unsuccessful blinding may lead to differing placebo effects between the active and control groups, potentially introducing bias into the estimation of relative treatment effects. Concerns have arisen regarding the overestimated effect sizes of psychedelics due to the issues of blinding and response expectancy. Psychedelic treatment is usually administered with psychological support or psychotherapy, and thereby the isolated pharmacological effects of psychedelics remain to be determined. Surprisingly, on July 1st, 2023, Australia approved psilocybin for the treatment of depression, the first country to classify psychedelics as a medicine at a national level. To date, only one blind, head-to-head randomized controlled trial has directly compared a psychedelic drug, psilocybin, with an antidepressant drug, escitalopram, for patients with major depressive disorder. This randomized controlled trial reported that psilocybin showed a better efficacy than escitalopram on the 17-item Hamilton Depression Rating Scale. Well, I don't blame anybody, but let's just say I have a lot of experience with a liquid diet, and that, like, pretty much it's like, yeah, pretty much my normal at this point, since I'm so accustomed to it, where, like, there have definitely been times in my life where I can literally only consume things in liquid form. It's like, yeah, my brain, like, has no problem with it, or, like, I've essentially been socialized or conditioned to accept a liquid diet. We aim to assess the comparative effectiveness and acceptability of oral monotherapy with psychedelics and escitalopram in patients experiencing depressive symptoms. Given that unsuccessful blinding can potentially lead to a reduced placebo response in psychedelic trials, we distinguish between the placebo responses in psychedelic and antidepressant trials. We also investigated the differences in patient responses between people who receive extremely low-dose psychedelics as a placebo and those who received a placebo in the form of a fake pill, such as niacin in psilocybin trials. Our study allowed for a relative effect assessment of psychedelics compared with placebo responses observed in antidepressant trials. Well, I don't necessarily want to compare, but I'm transparent about the fact that I have Crohn's disease, and that I've had about 3 feet of my small and large intestine removed, which poses, some challenges sometimes. And so it's sometimes a liquid diet is definitely a quality of life improvement, for sure, at times. So not going to dissect their methods, study selection, eligibility criteria, etc., etc. Okay. Okay, and forest plots. Let's go right to their discussion. Principal findings. This network meta-analysis investigated the comparative effectiveness between psychedelics and escitalopram for depressive symptoms. Firstly, we found that the placebo response observed in antidepressant trials was associated with greater effectiveness than that observed in psychedelic trials. Secondly, when compared with placebo responses in antidepressant trials, only escitalopram and high-dose psilocybin were associated with greater effectiveness, and only high-dose psilocybin exceeded minimal important difference of 3. Notably, the effect size of high-dose psilocybin decreased from large to small. Thirdly, among the included psychedelics, only high-dose psilocybin was more likely to be better than escitalopram 10 mg or 20 mg, exceeding the minimally important difference of 3. Fourthly, in patients with major depressive disorder, escitalopram, ayahuasca, and high-dose psilocybin were associated with greater effectiveness than placebo responses in antidepressant trials. However, only high-dose psilocybin was better than extremely low-dose psilocybin, exceeding minimal important difference of 3. Taken together, our study findings suggest that among psychedelic treatments, high-dose psilocybin is more likely to reach the minimal important difference for depressive symptoms in studies with adequate blinding design. While the effect size of psilocybin was similar to that of current antidepressant drugs, showing a mean standardized mean difference of 0.3. I know I've seen this before, or I know I've read it before, but I'm curious, in the studies, or at least in some of the studies, I'm sure it's not the same all across the board, but I'm curious how their sourcing and, let's say, whatever, processing their psilocybin. Methods, information. Okay, yeah. Well, yeah, I've highlighted. I know that I read before because I highlighted it. Psilocybin was obtained from THC Farm, so Frankfurt, Germany, and formulated into the investigational medicinal product 5 milligrams psilocybin in size 0 capsules. Blah blah blah. Okay. And I have no idea. In this study, whether 5 milligrams is high or low. I've never consumed a psychedelic in my life. That's an excellent question. What is high dose by their standard? Because I definitely couldn't tell you. Just I don't know what when people talk about microdosing with psychedelics. I don't know what they mean by microdosing, and as far as I can tell, there's no technical definition of microdosing. This is just more in the psychedelic world of this is what has been largely agreed upon by whatever recreational users to be microdosing. Psilocybin high dose greater than 20 milligrams, extremely low dose 1 to 3 milligrams. Oh, milligrams per kilogram? Well, I guess they don't have that. Well, okay, yeah, they converted to per 70 kilogram. Or a dose of 5, well, yeah, you can convert that to milligrams per kilogram. A dose of 1, or a dose range of 1 to 3 milligrams per 70 kilograms are used as an active control. Okay. So then it seems like, at least, in this study, the 5 milligrams, that's like, a moderate to like low dose, depending on the size or the weight of the individual. Okay. Oh, there's nothing to apologize for, Ronan. In a randomized controlled trial, treatment response was defined as the response observed in the active arm. Placebo response was defined as the response observed in the control brackets placebo arm. Treatment response consists of non-specific effects, placebo effect, and true treatment effect. Placebo response consisted of non-specific effects, therefore the placebo effect is not the same. Okay, yeah. Okay. However, in most psychedelic trials, blinding was either reported as unsuccessful or not assessed at all. For example, 2 trials of lysergic acid diethylamide reported unsuccessful blinding, whereas the trial of ayahuasca only reported that 5 of 10 participants misclassified the placebo as ayahuasca. Which, yeah, I find this super interesting. But again, I have zero experience with psychedelics, so I have no idea, like, how it feels subjectively. But at least from what I hear, or like the information that I get from people around me, it's like, it's apparently obvious when you're taking a psychedelic, but apparently for some people, like, it's not obvious. Of like half of the participants here misclassified the placebo as ayahuasca, and I know that the reverse happens. Like, people will be taking ayahuasca, and they think that they're getting the placebo. In trials of MDMA, participants' accuracy in guessing which treatment arm they were in ranged from approximately 60 to 90%. In the case of most psilocybin trials, blinding was not assessed, with the exception of the study by Ross and colleagues in 2016. In that study, participants were asked to guess whether the psilocybin or an active control was received, and the correct guessing rate was 97%. In our study, we established several network meta-analysis models addressing this issue, and we found that placebo response in the psychedelic trials was associated with less effectiveness than that in antidepressant trials. Therefore, the effect sizes of psychedelics compared with placebo response observed in psychedelic trials may be overestimated. All of the psychedelics' 95% credible intervals of the relative effects crossed 0 when compared with the placebo response in antidepressant trials, except for high-dose psilocybin. That dose of the research into recreational usage studies, 20 mg, would be about the equivalent of a normal cap being eaten for recreational use. So then I assume that's like your standard dosage of, well, yeah, recreational users. The comparisons between psychedelics and escitalopram show that high-dose psilocybin was more likely to be better than escitalopram. Psilocybin was usually administered with psychotherapy or psychological support, which, like, I think this is another thing that, at least in my mind, gets left out when people talk about, the research on psychedelics, and like the benefits, at least some of the benefits seen so far with psychedelics. It's very often coupled, okay, with, as they say, psychotherapy or psychological support. Just as in this one, okay, where they saw pretty dramatic effects, okay, or significant effects on the treatment for moderate to severe PTSD, but this is MDMA-assisted therapy, so it's not like, the participants are taking MDMA and, like, they're sent on their way. It's like, no, they're taking MDMA and like they're participating in like pretty intensive sessions, like over the course of like hours, or I think even sometimes like days. And so like this is a a pretty intensive intervention. Therefore, the greater effectiveness of psilocybin may be from not only pharmacological effects, but also psychotherapeutic support. However, we also found that high doses of psilocybin was associated greater effectiveness than extremely low doses of psilocybin. This effect also indicates that the effectiveness of psilocybin cannot be attributed only to concomitant psychotherapy or psychological support. Fair enough. In patients with major depressive disorder, ayahuasca, low-dose psilocybin, high-dose psilocybin, escitalopram 10 milligrams, 20 milligrams, were associated with greater effectiveness than the placebo response in antidepressant trials. However, when compared with extremely low-dose psilocybin, only high-dose psilocybin was associated with better effectiveness. The standardized mean difference decreased from 0.38 compared with placebo response antidepressant trials to 0.3 compared with extremely low-dose psilocybin. As such, the effectiveness of psilocybin should be considered with concomitant psychotherapeutic support in people with major depressive disorder. The effect size of high-dose psilocybin was similar with antidepressant trials of patients with major depressive disorder, showing a mean standardized mean difference of 0.3. Okay, and well, I'm not really going to go through the strengths and limitations. It's pretty much summarized in the article summary read earlier. But yeah, implications and conclusions. So what do the authors say themselves? Serotonergic psychedelics, especially high-dose psilocybin, appear to have the potential to treat depressive symptoms. However, study designs may have overestimated the efficacy of psychedelics. Our analysis suggested that the standardized mean difference of high-dose psilocybin was similar to that of current antidepressant drugs, showing a small effect size. Improved blinding methods and standardized psychotherapies can help researchers to better estimate the efficacy of psychedelics for depressive symptoms and other psychiatric conditions. And this is the overall summary of the article, what is already known, what this study adds. So, what is already known? Psychedelic treatment resulted in significant efficacy in treating depressive symptoms and alleviating distress related to life-threatening diagnoses and terminal illness. Meta-analyses have reported standardized mean difference of psychedelics for depression reduction ranging from 1.37 to 3.12, while antidepressant trials were approximately 0.3. No network meta-analysis has examined comparative efficacy between psychedelics and antidepressants for depressive symptoms, and effect sizes of psychedelics might be overestimated because of unsuccessful blinding and response expectancies. So what this study adds: to avoid estimation bias, placebo responses in psychedelic and antidepressant trials were separated. Placebo response in psychedelic trials was lower than that in antidepressant trials. Among all psychedelics studied, only high-dose psilocybin was associated with greater effectiveness than placebo response in antidepressant trials. Standard mean difference, 0.31. Among all psychedelics, only high-dose psilocybin was associated with greater effectiveness than escitalopram. Interesting. So it seems like, at least, based off of this, meta-analysis, maybe temper our expectations, which is, I think pretty normal when it comes to research on emerging therapies. Of like, they get hyped up, like, oh, this is the next big thing that's going to revolutionize, and then as more data comes out, we gotta temper our expectations, or at least, this is expected, at least, or I've gone through this a number of times when it comes to, emerging therapies for my own disease, Crohn's disease, of like, a certain pharmaceutical in the pipeline gets hyped up as like, oh, this is going to do it. This is going to like revolutionize Crohn's disease treatment. And then as more data comes out, it's like, oh, not as good as we thought it was going to be. and so maybe we need to like temper our expectations. But who knows? The research on psychedelics seems pretty exciting and potentially transformative. I think it's largely a matter of like finding the patients who can benefit the most of like a targeted approach. Probably, at least that's what my estimation would be. Let's see. I'm going through some of my psychedelic research. Use a lot of drugs when you trip LSD or roll. Daily, the hallucination effects wear off after a while. Instead, you just get mood altered. Well, I hope at the very least, mood alteration for the better, at least on average. Like, there's some interesting studies on, let's say, ketamine. Where, yeah, so just as, psilocybin is being explored for, major depressive disorder. But as of now, as far as I know, okay, electroconvulsive therapy is the most effective treatment that we have for either treatment-resistant depression or major depressive disorder. Where I believe there was like sort of a head-to-head or like a comparison. Electroconvulsive therapy versus ketamine for treatment-resistant depression. Where, electroconvulsive therapy, most effective treatment for major depression, and the gold standard for treatment-resistant depression. And it seems like, ketamine might be as good, maybe, at least based off of some of the emerging research. Seems to hold a lot of promise. But again, from what I can tell, based off of the research, there might be some potential safety concerns when it comes to, treatment with ketamine. But, I'll leave the experts to answer those questions. But that's just my understanding. Very rarely after a stint tripping or rolling did you feel like shit and depressed. If you did way too much and are dealing with the after effects of serotonin. Yeah, fair. Like, I definitely know, at least based off of what I heard from other people, it's like, whatever, psychedelic use can be really transformative, like in a positive way. And also on the rare occasion, it can be transformative in like the most negative way. Although I think that's, more rare, but it can still happen. So there's understandably a lot of things come to mind when electroconvulsive therapy or electroshock therapy is, invoked as a result of, how it's been used in the past and, depictions in media. Yeah, exactly. This is not to say, I've never observed it how it's done today. So, I don't know whether it's a walk in the park per se. But yeah, I'm highly confident in how it's done today. It's not how it was done like, 50, 60 years ago, and not how it's depicted in the media. And typically, as far as I know, this is generally done as like a last resort. Like, we've tried most other things, and since this is like the most effective and the gold standard, once we've largely run out of options, then we will go down this road. Yeah, exactly. Like, and that is at least that is borne out in the data that I have seen. Well, data like this, and as they explicitly say, most effective and the gold standard for treatment-resistant depression. Oh my goodness. Yeah, I'm super sorry to hear that. Which it's like, that's why, like I said, I have zero experience with psychedelics, and that's largely because, not that I'm not curious, but like I'm pretty much too scared to try them. Pretty much just like a coward, I guess. Where, yeah, I'd rather not take that gamble. Like, yeah. Like, unless I can actually see some sort of therapeutic benefit, I prefer, you know, I generally err on the side of caution when it comes to most things. Yeah, exactly. Generally is the last resort. Where, you know, I'm pretty sure this is like a rare, really horrific outcome when it comes to psychedelics. But I know that it does happen sometimes or on the rare occasion, which is unfortunate. That's why, you know, I think when it comes to psychedelics, like finding out who the appropriate patient is going to be like really key. Like who is at risk of having a really terrible outcome when it comes to psychedelics. Hopefully we can answer that question. So, well, I think I covered just about, well, I technically didn't cover everything that I wanted to cover. I wanted to cover this paper on chronic fatigue syndrome, myalgic encephalomyelitis, but I'm going to save it for this weekend, probably Saturday. Like, I definitely, like, for sure I'm going to cover this paper, and I plan to cover it on Saturday, if not Sunday, because this is a really cool, I think it's a really cool paper that has, you know, that's related to a disease and condition that is, let's say, interesting from a research perspective, where there's a lot of mystery, at least in my mind, around chronic fatigue syndrome. But yeah, got through the biochemistry lecture, and so yeah, I'm doing the biochemistry lectures solo, at least for the foreseeable future, but still plan to do weekly on Wednesdays, pretty much at the standard time. I'm going to schedule it. I might maybe change the day, but either way, I'm going to schedule it like on YouTube as an event and all that stuff, and I'll probably put it in my Twitch schedule as well, so that it's like locked in. But pretty much covered mostly everything that I want to cover, at least bare minimum, was the biochemistry lecture. Slowly and surely getting through the biochemistry stuff. Yeah, I'm definitely not a clinician or any expert whatsoever in the treatment of any condition. But like, yeah, I would definitely be suspect if electroconvulsive therapy was like the first line of treatment. God helmet to help us do more patient neurology scans. Yes, absolutely. And I think we'll get there, almost certainly. Our knowledge of the brain, you know, is, I think, increasing pretty rapidly. I was apparently highly insane, even poor, and did psychedelics and hard drugs all the time. It's not like this was... Oh, okay. Fair enough. Either way, still a very sad outcome, which I'm sorry to hear. Oh, we got a solicitation. What? I'm gonna have to dust off my copy of the Divine Comedy, which I have. I have a good quality copy of the Divine Comedy. One of these Saturdays, I absolutely will pass by. Mark my words. But yeah, that's gonna be it for me for this evening. I will be back either Saturday or Sunday. It should be Saturday. I will, as usual, update the Discord. Feel free to join the Discord. Let's see. Yeah, there's not really anybody to raid at all. Not really in science and tech. So, going to end it there. Want to thank everyone who passed by. Ronan, thank you so much for passing by. Great to see you. It's been a minute. And Jack, Bob Marley, and Gina Jake, I believe. Thank you for the follow. Nice to see you. Happy to have you here. Yeah, I believe I saw some of the updates. Like, well, I saw something that you weren't able to do it this past Saturday. But I know I think you do it Saturday mornings. So I do plan to pass by one of those Saturday mornings. But yeah, thank you everyone. Thank you, Bob Marley, for passing by. And yeah, I'll be back. Should be back on Saturday, if not Sunday. Until then, take care and be well.